Good morning. Do you able to see my presentation?
Yes, sir.
Okay. Thank you. Let us start. On the last class, we discussed regarding the parsing table construction, and in that construction process, we also demonstrated that when it is LALR0, means there is no look ahead information available, then at times, based upon the production rule or the grammar in general, it is possible that we will encounter one situation which leads to shift as well as reduce operation. So as you remember that there are 5 operations in total according to parsing table: shift, reduce, accept, go to, and some error state. Now to avoid the shift reduce conflict, so we proposed that let us go for SLR 1 parser. Now in case of SLR 1 parser, as I demonstrated here, I will go into details. Whenever there is a situation of the shift reduced conflict means that one particular matrix cell in the parsing table suggests you can shift or you can reduce. Now when the suggestion is for both, then it is really a confusion which one to take. Shall I go for shift or shall I go for reduce? The suggestion which is accepted by SLR1, which is more stronger than LR0, is that for the conflicting cases, you follow the follow of that non-terminal. So let us consider this grammar. We call this as G9. Now there are 5 production rules, and you know the drill that 0th production rule will be augmented S prime derives to S. Then if I construct the states from these production rules, then I will start with the 0th production, S prime derives to S. So on the left hand side, I put a dot and I will get 0th state, which I am denoting as I0. So S prime derives to dot S. Now you know, as per the closure properties, since the dot is on the left hand side of the non-terminal S, so all the production rules which derives S, that is production rule 1 and 2, the first item of those production rule will also be part of this. That way I am getting the second and third item here. You can see that they are nothing but the production rule 1 and 2, where leftmost position on the right hand side there is a dot. Now from the second item, you see that dot is appearing on the left of L. So again, by the transitive closure property, I will include production rule 3 and 4, where dot is placed in front of star R and in front of ID. Now for the third item, which is part of state I0, dot is appearing on the left of R. So the 5th production rule will also be added in state 0, where dot is on the left hand side of L. Since you already included the production rule 3 and 4, so because of the inclusion of the last item here, there will be no further changes. And that will give you the 0th state here. Now if I start with the first item, and if I move the dot from the left hand side of S to the right hand side, then I will get state 1, which means upon realizing non-terminal S, from state 0 I will go to state 1. When I see L, then from state 0 I will move to state I2. And when I will see L, then from the state 0, it is the second item and the last item, both will go to state I2. From I0, if I see R, then on non-terminal R, the transition of I0 will be to I3, state 0 to state 3. Then if I see terminal multiplication or star, then I will move from state 0 to state 4, the first item of state 4. Now you see the first item of state 4 indicates that dot is on the left hand side of R. So production rule 5, the first item of that is R derives dot L, will be included here. Now dot is on the left hand side of L. So following the closure property, third and fourth production rule will also be included in I4. Similarly, I believe you can complete the total states and their respective transitions. Okay. Now, once you are done, then I will suggest you to look at the situation of state 2. What is there in the state 2? In the state 2, there are two items. S derives L dot equals to R and R derives L dot. Now here is the situation. If you are in intermediate situation of parsing the string and you identified that on the left hand side you got L, and currently your position is here, and if you are at state 2, then there are two possibilities. One, you can shift dot for this assignment operator, or you can reduce following the production rule 5, that is the second item of state 2. Hence, there is a shift reduce conflict. We don't have look ahead information now. If we incorporate the following information, then we see that assignment operator belongs to follow of R. How? So look, first production, it doesn't say anything to you, but there is one R. So L equals to R. And this L production, L following the production 3 can generate star R. And if it generates star R, then after R, this assignment operator will appear. So this assignment operator will follow the non-terminal R, and hence this is that assignment operator is part of follow R. Since the assignment operator is part of the follow R, then if you follow that one, then perhaps you can avoid the conflict. You can note that the grammar is not ambiguous, still there is a conflict, which says that SLR even is not powerful enough to remember enough left context to decide what action the parser should take on input equals to. To resolve this, we built LR1. The modification for LR1 we have done here. This is sample grammar G7, and we augmented by incorporating the first zeroth production rule, S prime derives to S. And when we incorporate this one, then one non-terminal S prime and one terminal dollar is also incorporated in grammar 0. Now in LR1 parser, unlike to 0, here the parameter kind of thing, or within parentheses it says 1, which means there is a look ahead information available. Okay, so before going to the theory, if I give you an example, say for this production rule 2. So for production rule 2, so I know small c and capital C, that is one item. I know C dot capital C is one item. I know C dot is one item. This is what we studied in LR0. So corresponding to production rule 2, I am having 3 items. Now LR1 incorporates the information of look ahead information. Along with this, I am adding C information, small c, terminal, that is my look ahead information. That when, say I am at this item, the first item, I am marking with this double arrow, then if the dot is here, then I will move, say when I will see A dot C, then I will make a move. So this extra part is my look ahead, and since I mentioned LR1, so look ahead is 1. Only one terminal symbol will be in my look ahead. You remember that in one Venn diagram we have drawn, we mentioned that LRK in general, where k is an integer variable, an integer constant, varies from 0 to any number. Now k equals to 0 we consider, that is LR0. Now in LR1, I am suggesting one look ahead information, and that look ahead information will also be incorporated as part of the item. After the item, using a comma, I will write that one. And the look ahead information will be terminal symbol. Okay. Now if I go back to the theory part, then it says that an LR1 item has the form A derives alpha dot beta. There is a dot in between alpha and beta. So here, comma A, small a italics, which means the small a italics is a terminal. So this is terminal symbol. Where A derives alpha beta is a production and A is a look ahead symbol. So that look ahead, that terminal is my look ahead symbol. This look ahead can be any terminal symbol or dollar. Although we consider dollar as a special kind of symbol, but the property of dollar is kind of acting like a terminal. I'm not telling that is terminal, that is of course special, but kind of. As the dot moves through the right hand side of the production, token A remains attached to it. So that way LR item will be like this, calls for a reduction operation. Why? Because for this you see that dot has reached at the end of the production rule and look ahead still is A, which means during parsing the string, if I see that I have reached to one position where on the left hand side there is alpha and my look ahead is A, then I will reduce. Now you can remember that previous case where there is a confusion that so L dot was one situation, another was L dot equals to R. So I was confused which one to take. So this indicates reduction and this indicates shift operation. Now LR1 resolves that conflict by telling that if A derives alpha dot is there, so if both are present, now the decision will be taken based upon my look ahead symbol. If look ahead is A, then you reduce. If look ahead is not A, then so here you can see that assignment operator, then you shift. So this is called for reduction action when look ahead is A. So for examples it is given. Now what will be the modification in my closure property for a non-terminal? Now you incorporated one look ahead information, that is terminal T. Small t is written here. Now if I assume one item A derives alpha dot B beta, dot is in between alpha and capital B. So on the right hand side, capital B is non-terminal. Alpha and beta both are union of terminal and non-terminals as per our convention. And if that item belongs to say one state, then I have to look for all production rules. B derives gamma belongs to G, that complete grammar. Okay. Now you remember previously for LR0 closure, if dot B is there, then all the production rules B derives gamma will also be considered. The first item actually is also be considered as part of this item as a closure property or state as a closure property. Here no further screening is required. But when I have a look ahead information LR1, then I am checking further that for each token small b, that is each terminal actually belongs to first of beta t. So which one is beta? If you look at the item, then beta is occurring right after b. Now it suggests that if after b, so after b, beta is occurring. Now if I consider the first of beta, you remember that first indicates that upon derivation which will occur at the first of the right hand side of the production rule. So when I consider at this line, when I consider terminal B belongs to first of beta t, then I am ensuring that this terminal or token B will occur right after B, isn't it? If it will occur right after B, then you try to understand the situation that when it will occur right after B, then it suggests that when I will see B, then instead of shifting, you reduce to B, because first B will complete, then beta will appear. So what you see here is that it is not, first of all, it is not all the production rules where B derives gamma will be part of the item as per the closure. But all the production rules for which the next non-terminal will say that what is the first of that, or I will identify the terminal symbols which will occur after B. So for all items, B derives gamma where the look ahead symbol belongs to first of beta t will be part of this state. Is this point clear? So here I am writing, say, A, alpha, B and beta. Now my initial dot was here. Previously that indicates, since dot is on the left hand side of B, so all the production rules starting with the B will be part of this as per the closure property. Now I suggest, okay, do not go for all of them, but you check that after B who will occur. So after B who will occur? All those terminal symbols which are first of this beta. So first of this beta means it will be at the beginning, and beginning means just right after this B. Now if they are occurring just right after this B, which indicates that if my dot is here and these first terminal symbols are my look ahead, then I will reduce to B first, then I will move. So you see that as per the construction of this closure, I am ensuring with one look ahead that shift reduce operation, that shift reduce conflict can be eliminated. Now closure is computed transitively, so others will also include following this one. And for this particular grammar, as you can see that there are possibilities for this product from production rule second and third, that look ahead can be C or D. So if dot is placed here, so one situation is this production rule, another is this one. That's why here you see that in the item, so C derives small c, terminal C, dot capital C, non-terminal C, comma, in look ahead C or D. C or D is used. Okay. Now following this, if I draw the parsing table, then what will happen? So this is my G7 grammar. There are 3 production rules only. I will add one more. That is my 0th production rule. S prime derives to S, and I will assume that dollar will be at the end of this. I will assume that one explicitly, you need not have to write. Now my 0th state will be S prime derives to dot S and look ahead is dollar. Now following the closure property, item 2, 3 and 4, I mean production rule 1, 2, 3, those will be added. And when I am adding, as I mentioned, for production rule 2 and 3, so look ahead is C or D, that's why I am writing C/D. Now from here, if I see S, then the transition will be S prime derives S dot, look ahead dollar, that is also my accept state, that is my I1. If I see C, capital C, non-terminal C, then I will move on to I2, and following the closure property, production rule 2 and 3 will come, but here the look ahead is dollar. If my look ahead is C, if I will transit on C, then I will go to I3 and accordingly I will form the state. So I am not going in details. So if, I believe that as of now what we have discussed, based upon that one, you can able to figure out how this state transition diagram has done, and accordingly how the state has been constructed. Okay, if you have any problem you can tell, we will discuss it. Next we will move on to more powerful, and actually that we will implement LALR1 parser. It is the same grammar G7. Here the augmentation is done at the 0th position or 0th production rule. LR1 states, so first we have to construct the canonical LR1 parts table. Now what is the modification of LALR states over the LR1? Two or more LR1 states having the same set of core LR0 items may be merged into one by combining the look ahead symbols for every item. So one after another I am going through this. What does this mean? Core L0 item, core LR0 item. It says about the production rule only as the item, and there is no look ahead symbol. Yesterday we discussed the construction of LR0 items, LR0 parsing table. You remember that one. The addition today we have done when we are looking for LR1 is after that item, or I am making that as part of the item. So after the production rule, comma, one look ahead information I added. Now it suggests that if I go back for this state, and for this state, you look closely. If I do not consider the look ahead information, which means after comma whatever it is, in state 3, this is my state 3 and this is my state 6. In state 3, after comma C or D is there in for all the 3 items. In state 6, after comma dollar is there for all the 3 items. Now, if I do not consider that look ahead information, that is, I ignore comma C/D in state 3 and comma dollar in state 6, then you see both the states are same. And you also admit that now they are LR0. There is no look ahead information, only the item. Any question here? It's simple, right? So look ahead symbol was added with a comma, and since it is LR1, so only one look ahead symbol was there. In state 3, it is C or D, so C/D was written. In state 6, it was dollar, so dollar was written. But if I look at the production rule only and assume there is no look ahead information, so dollar will not be there in state 6 and C or D will not be there in state 3. Then you see the production rules are same for state 3 and 6. And that is also my LR0 state. Now I am going to next slide. It says that core LR0 items are same. Right? So having the same set of core LR0 items, right? Then it says that if it is the situation and they differ only by the look ahead information, then probably you can merge them, merge those two states. And what will happen? I'm going to previous slide. For state 3, it was C or D, the look ahead information. And for state 6, it was dollar as the look ahead information. Since the core LR0 items are same, So if I am allowed to merge state 3 and 6, then I can write C or D or dollar. So if the lookahead is C or D or dollar, then I can have this set of items. Going to next slide. That is what is suggested in the construction of LALR1 states. Two or more LR1 states having the same set of core LR0 items, which means that do not look at the look ahead information, whether the rest of the items are same for two states, then may be merged into one by combining the look ahead symbols for every item. Transitions to and from these merged states may also be merged accordingly. All other states and transitions are retained or remain same. That way, for that previous example of LR1, which is following this G7 grammar, state 3 and 6 can be merged and state 4 and 7 can be merged. So here it is written in state 3 item, you can see that what was the item. So LR0 was same, the look ahead was C or D. State 6 LR0 was same with state 3, look ahead was dollar. That's why after merging, the LR0 or the items for the core LR0 remain same. The look ahead is now C or D or dollar, which was C or D in state 3 and dollar in state 6. Again, for state 4, if I go to the previous slide, state 4 and 7. State 4 is where? This is my state 4. So here it is C derives D dot. And my look ahead is C or D. And 7 is what? Here is my 7. This is my 7. And this is my 4. So it says C derives D dot and look ahead is dollar. Now LALR1 construction suggests you combine 4 and 7, and since the core part C derives D dot is same, then you have one something like C derives D dot comma C or D or dollar. Okay. Now coming back here, this is what is done here in the second part, the merging. Now when we are moving to LALR1 and showing the power of it, I am also eager to tell you that since we are merging, then there will be no shift reduce but reduce conflict. When say we are at position C derives D dot, so which production rule to take? In some grammar that may be a problem. I will show you that later. But before that, let us see that after converting LR1 to LALR1, so how will it look like? So this is the parsing table for LR1. And as we suggested, 3 and 6 was merged or combined, and they are marked as 3, 6 here. 4 and 7 are merged again, and they are merged here, 2, 4, 7. So this is my LALR1. Further, 8 and 9 was merged. This is my 9 and this is my 8, and that is actually this one. Okay, so here is an example of class. So from LR1, so for this grammar, say G10, which is given here, and set of production rules, we first computed LR1 parser, and it is my LR1 parser here. And then I convert that one to LALR1 parser, and when I am converting, then I am merging. So you see that merging is done for 6, 7. So again, I am not going into details. You will please work out and check this one. If you have any confusion, let me know. We'll discuss them. Okay, because we discussed enough parsing table and construction of this. Now this kind of situation, you see that is creating the reduce conflict. This is one practice example you can consider. So here is more prominent here that shift reduce conflict and reduce conflict between B derives xy and E derives xy on input C. It was taken from that previous slide. Now few facts is that an LL1 parser would be confused, but at the X, should it expand to A to B, C, D, or to E, F, S, as both can start with X. And LL2, LL3, which means when you will keep on increasing the look ahead information, then it may resolve, would have similar problems, but sometimes it may not resolve. Now, if I look for LR2 parser, so LR parser with 2 look ahead information, would be able to also see that D or F that followed the C, and so make the correct choice between B and E. So from here also it is clear what we have shown you through the Venn diagram, that LR parsers are powerful compared to the LL parsers. Now LL4, so LL parser with 4 look ahead symbols would also be able to look far enough ahead to see that D or F that follows C, and so make the correct choice between expanding A to B, C, D or to E, C, F. Okay, so if you keep on increasing the look ahead, then you can able to resolve the conflicts, either a shift reduce or reduce conflict. But somewhere we have to stop, and we decided that we will provide some restrictions. With that, we will have only one look ahead information, and we will work with that one. Okay, so this is just an example. So I am not going into details. So this is with LRK. So the grammar would confuse any LRK or LLK parser with a fixed amount of look ahead. So to work around, so you can check this one. And that completes our module 3 discussion on the parser. Now we will move on to the module 4, that is parser generator. But before that, do you have any question? Okay, then let us take a small break of say 5 minutes before going to the next module. Okay, so after 5 minutes we will start the next module. Let us continue. In this module 4, we plan to discuss the Parser generator. This module will be useful for your assignment 4 in laboratory. So assignment 3 will be released in this week, and assignment 4 will be released later. And I believe that all of you has sent your group information correctly. We finalize that group information, and on the next class, day after tomorrow, laboratory class, when we will release our assignment 3, 3 onwards, the group formation is required. So we will release that information also. So main purpose of this module is to understand the Yacc or Bison specification. So although we will be using the syntax, which is mostly Bison specific, and in laboratory class also we will focus on Bison, which is powerful than Yacc, but it can also be used for Yacc. So understand parsing by parser generators. Primary objective and outline we will discuss first, then the Bison specification. Similar to the Flex, Bison is also has a similar specification. Then we will work out with simple expression parser where there is no variable or identifier or assignment statement, just the evaluation of expression. Then we will move on to simple calculator. And in the programmable calculator, we will discuss when the variable will be there, assignment operation will be there, and it might be possible that you are entering multiple expressions and it will be computing that one. So those things we will discuss. And finally, some ambiguous grammars, its effect on expression, programmable calculator, and what you studied, the dangling else. So in PDS class. So in the context of parser, and what will it be actually when a compiler is parsing, and that thing also we will discuss. So if I look at the different phases of the compiler, we finished the discussion on the scanner or the lexical analyzer. Now we are in the process of doing a syntax analysis, which is nothing but write a parser for a simple expression grammar using Bison. In detail, we have discussed the parsing technique, and we mentioned that LALR parsers are more powerful and Bison implements LALR1. So given a grammar, how to construct the parsing table, that we have discussed. But good news here is that unlike to say RD or recursive descent parsing process, where if you remember that corresponding to each non-terminal, we had to write one function. Additionally, two more functions, one is main, another is match function was there, and using that one we are able to do that parsing process. But for Bison, good news is that directly you can write the grammar, and most of other stuff will be taken care of about the Bison utility. Similar to that scanner that you have wrote, that you just mention that what is the token pattern in the token stream, and the Alexa will take care of the rest. Then for the semantic analyzer, we will extend the parser for expression grammar semantically to build a simple calculator from expression grammar and to build a programmable calculator from the simple calculator, which contains the identifier, storage, semantics, etc. Like Flex, so this Bison also has 3 sections separated by, if you remember, 2% symbol starting from the beginning of the line. So this symbol we place twice, and that way we are getting 3 positions or 3 sections rather, definition, rules, and 1 auxiliary sections. For Bison, terminal symbols are like numbers are identified by percent token. I will go to an example shortly. Usually, but not necessarily, these are multi-character. So multi-character means it includes digit also. Single character tokens like within single quote addition may be specified in the rule simply with quotes. Non-terminal symbols like expression are identified by percent type. So two things we learned here. If it is terminal, usually it is denoted by percent tokens, and if it is a non-terminal, it is usually denoted by percent type. Any symbol on the left hand side of a rule, by rule it is the production rule, is a non-terminal, because that production rule will be translated here directly. Now the production rules are written with left hand side non-terminal separated by a colon. So when in the production rule say S derives E, so this derives or arrow will be replaced by colon from the left hand side symbol. Multiple rules are separated by alternate. This is same as the convention we are using for the production rule in grammar. Epsilon productions are marked by empty right hand string. So which means for this S to E, if I write something S E, that is my production. Now if there is one epsilon production, then it will be S colon semicolon. Nothing is there. Set of rules from a non-terminal is terminated by semicolon. So here it will be terminated by semicolon also. Non-terminal on the left hand side of the first production rule is taken as the start symbol by default. So that was our assumption, and it is true for everywhere. You know that otherwise you need to specifically mention that what is your start symbol. Just to avoid that one, it might be a good idea that you assume that first production rule left hand side non-terminal is your start symbol. That's it. Start symbol may be explicitly defined by %start colon %start statement. So it may also possible like this way you can define. Now the first expression grammar. Here you see that it is same as what we have discussed so far as an grammar. Extra part I am marking here is this. Now you can consider statement derives expression. S is my start symbol. Expression equals to expression addition T, expression subtraction T, or expression can be a term. T means term. T derives T multiplication factor, T derives T division factor, or terms derives factor. Now factor derives to within parenthesis E expression. Factor derives to this is the unary minus operation, or factor derives to some number. This is the integer constant. Now you see we have covered unary minus, addition, subtraction, multiplication, and division. We covered parentheses, and also if you look at this expression grammar, then you will understand that we covered the priority of the operators, or operator precedence is also mentioned here. Because when we will do say that bottom up parsing, then we will start from some number or some terminal like some operators, addition, multiplication, etc. And then during the derivation and reaching to the start state S, first we need to go through multiplication or division, then we will go for addition or subtraction. And we will also assume that existence of a dollar at the end of the expression, indicating that end of the string that is necessary. This is the flex specification. As you remember from our previous lectures, usually the legs of flex files are saved as .l. So here you can write say calc.l, that is my lex file. If you remember, this is one marker or different separator, this is another separator. That way you have section 1, section 2 and auxiliary section 3. Now previously we used to write the pattern in section 1 here along with some C functions. Now here what we include y.tab.h. Now this y.tab.h is one header file. It will be generated by the Bison program. If you remember the flow of the Flex and Bison in order to generate a .out, I will show you today also one such diagram, the same diagram actually. So this y.tab.h you need not have to write. So it will be generated by the Bison from the program, and during the linking process you need to include that. That's why you included it here. It also doesn't exist already in your system. Now this is math.h. So if some math specific calculations you need to do, then you need to include that one. Okay. Now you remember that in first part or section 1 we included the pattern, and corresponding to that pattern what is the action, that was in my second. We also mentioned that instead of mentioning the pattern directly, we can mention the pattern as well as the action, and that is what is exactly done here in section 2. So pattern 1 through 9, this plus is actually on top of positive closure, and this star here is knee closure. But you know that subscript, superscript, that we cannot write in program. That's why the convention is like this. So starting with 1 through 0 and any number of digits, that will give me the number. So if it is the pattern, then I will return number. What is number? I will come to that one. As of now, I didn't define what is number. If it is space, so you see that within square bracket, /t is given for tab, and /t is given with a space. So space and /t, if it is there, no action. That's why this is actually, this is semicolon. I mentioned that if it is a epsilon production or no action is required, then just write semicolon. So it is the semicolon. When it is dollar, the character that indicates end of the string, so return 0. End of the input. If it is /n, new line, or pipe, dot, any character other than these digits or white space or tab or dollar, then I will directly return that text, YY text 0. This YY text, you remember that it is an utility inside the Flex program. So you need not have to worry when you will compile this using Flex. Then corresponding to this YY text, the relevant source code will be invoked and it will be replaced here. Now you see, it's very simple. The conversion of say one grammar to a Bison specific language. The file name we gave calc.y. So you see this .y indicates it's the Bison program. So Yacc also you can use, that is .y. Now these are my production rules. And what will be my program for Bison? Very simple. So here string.h, iostream, those C header file I included. This YY-lex, you remember this YY-lex was part of the Flex program. If I use that one in this program, then I have to mention that it has declared and defined somewhere, it has defined somewhere else. That's why extern int YY-lex. And the linking will be deferred until the lex program will come or Flex program will come. Then I am writing void YY error character star S. So these are some C declaration and definition part. Again you remember. So this is one marker and this is another marker. Section 1, section 2 and section 3. Section 3 is for auxiliary functions and section 1 is for declarations. Now this number, you remember I am going to the previous slide. So let me erase everything. So here I said that number is not known right now. This is .l or flex program. Okay. Now in .y or Bison program, I am declaring number as %token. You remember what was %token? The number. Okay. So %token number that I am declaring in section 1. In section 2, it is completely the production rules I have with me. What is the convention? How I am writing that one? So corresponding to S, I am writing statement colon. Colon is for all this arrow. So arrow is substituted by colon. Statement colon E I am writing as expression, and this production rule ends with a semicolon. So here there is a semicolon. Clear? Next production rule 2. E derives E plus T. E was expression, so I am writing expression colon E plus T. E is my expression again, T is my term I am writing. Now addition operation or that plus symbol is my terminal. So for that terminal, here I am writing within single quote plus. Now please note it down. I am just writing my production rule in the Bison specification. As of now, I didn't mention regarding any action. That plus means you need to add, those things I didn't mention. I will come to that later. But I am just writing the production rules in the format of the Bison specifications. Now production rule 2, 3, 4 all are derived from E. So this 2, 3, 4, you know that I can write like this. E derives E plus T or E subtraction T or just T. Agreed? Now I am doing the same thing here also. Expression colon, expression addition term, this pipe or vertical line indicates that OR operation, expression subtraction term or just term. And finally there is a semicolon. This is my semicolon. It indicates end of my production rule. Clear? Similarly, production rule 5, 6, 7 are converted, are translated here like this. Term multiplication factor or term division factor or factor followed by semicolon. Similarly, production rule 8, 9, 10 are converted as factor colon. So this left parenthesis and right parenthesis, you remember both are terminals. So that's why both are inside a single quote. Inside that left and right parenthesis, E is the expression that is my non-terminal. I am writing it here. Or unary minus factor. F is for factor, or num. Num is my digit, that is number, and number is also declared here. Additionally, I mentioned number is a token. You also agree with me that this token we discussed in the context of scanning process. That is the end of the section 2. In the auxiliary function, I have two functions. One, void YY error. So if there is any error, I will report that one. we will see one such error which will occur in this production rule also, which is easy to catch and easy to report. We will do that one. And then, of course, main is there. Now, in the main, there is only one function, that is YY parse. Regarding this YY parse, the definition of YY parse or declaration of YY parse is not in this file. C compiler do not have that one. It is the Bison utility, similar to YY-lex for our flex program. We expanded and we demonstrated to you that if I expand YY-lex, then I will get a series of codes written in C. Then it will be compiled by C compiler in order to generate the final executable file. Similar to that, Bison utility will expand this YY parts. You need not have to worry. Otherwise, everything, if you need to code in, say, C programming language, then it's a huge amount of time. But you see that this production rule, everything is coded by only this many number of lines. Now, if you call Bison with this calc.y, assuming that you name your function, you name your program source code as calc.c, cal.y, then it will be expanded to some C program. You can compile using C compiler and you can execute, right? Now, I know that not all the things are ready for execution, because I just wrote that addition operation, subtraction operation, and they are within single quote, indicating that is terminal. But what is the action related to that one? I didn't mention you that. That I will do. So this is what we have mentioned, some note on Bison specification. We mentioned this one. The same thing we have used, single character token like addition may be specified in the rule simply with quotes as of now. Symbolized terminals like number are identified by %token. Non-terminals like expression are identified by %type. It has not yet come. When we will consider the identifier or variable, then it will come, this %type. But we have seen %token. So that is the symbolized terminals which are identified by that. Rest of the thing we discussed. Now, for this simple calculator grammar, this is the grammar which was implemented in calc.y. So we need to bind its value to a constant terminal symbol, and we need to bind its value to an expression non-terminal symbol. So those two things are largely pending. So what we did, just now what we did, you remember that for S we write statement. Instead of this arrow we give colon. For E we write expression semicolon. For this E derives E plus T, there was no action item. So expression colon expression within single quote addition term. That was the thing was mentioned. But when it is actually an expression and actually a term, then how to add them, and in order to get another expression, those bindings are not considered or explained. That I will do here now. What it is doing, you see that first of all, let us identify the similarity with the previous calc.y. Then we will go to extra part. So this part is exactly same as the previous one. Okay. Now there are some changes here. I will come to their last. It was statement colon expression semicolon. It was expression plus term. This was not there. It was not there. The rest was there. Here also it was not there. It was not there. It is not there. It is not there. It is not there. It is not there. And it is not there. You see, rest of the things was there. And also it is not there. This is there, but this part has changed. It was not there. So only statement colon expression, addition term, or statement expression colon expression subtraction term or term semicolon, then term colon term multiplication factor or term division factor. So those things were only mentioned. Now what extra thing we have done is that now, as I mentioned in the previous slide, I am going here, that type non-terminal symbols like expressions are identified by type, and symbolized terminals are identified by token. I am going to that slide. Here, this token for number and for expression, term, and factor, those are the non-terminals. For that type. Clear? So that is the addition. Expression, term, and factor was not there. Now I am adding that one as percent type because I will have some action. I am going to write that one. That's why I am adding that. Now, similar to the flex program, if you remember that we attach corresponding to say each token, we attach some integer value, and then instead of bearing that name or the pattern as a whole, we were considering the integer values. Similar to that, here also we are having one placeholder value, int val for all of them. But instead of defining say one integer value for number type, for expression type, for term or factor, we are defining everything as part of the union. So whenever it is required int val, so it will pick from there. From the class of your programming and data structure, you understand that there was two user defined data structures, structure and union. So union is advantageous in a situation where say we need to use different data types, but only one out of them will be used always. Then instead of having all the data types, we can take the union because I know only one data type will be used at a time. And from there, the C compiler will also, instead of having all the data type, instead of having storage for all the data type, will have the storage for the largest data type, and it will typecast the required data type whenever it is required. That was the union for C programming. Similar to that, some concept is used here, and you see in the declaration part, initially it was percent token number. Now I am giving some int val, and for all the non-terminals, expression, term, factor, so I am giving percent type with some int val. Although I agree that for the statement, I am not giving any type because statement is kind of start state here and it is occurring only once. And when I reach to the statement, then I am done. So no need to carry that information further. That's why I am ignoring that one. But if you want, it's up to you. Now, the action I am adding with the statement is like this. Statement colon expression. You remember that production rule was S derives E. Now, if you remember the parsing table, then the reduction for this in LR parsing is that when I will have one E, then I will reduce to S. So the reduction means that whatever is there in E, I will print that one. So print equals to %D $1. $1 means that in my string, so the first one, so either terminal or non-terminal, is considered as $1. Okay, so I am printing that one, and that is my action for expression. Now you see where I am attaching that one and what is my syntax. Initially it was statement colon expression semicolon. Now I am doing after expression within opening and closing brace, printf statement is there, and which one I am printing? $1. Why $1? Because on the right hand side it is only E, so my terminal or non-terminal only one is present, so I am printing that as $1. Now for the second one, it was expression colon expression within single quote addition term. So which means the production rule was E derives, if you remember, E plus T, right? Now what will be my action? If I am storing that information in the variable expression on the left hand side, then the name of the variable will be $. Okay, and what I am doing, expression addition term on the right hand side, the terminal and non-terminal, so marking is 1, 2, 3. In this case I mentioned $1 because this is only 1, that's why $1 was printed. Now expression derives expression plus term, the action will be, so this E is $1, addition is $2, but I do not need to have that one because I know it is addition. Instead I will go for term, term is my $3. So I am adding $1 and $3 and storing that information to $. $. Indicates the current one. That is my expression here. Simple. And this action is within the brace. That is the syntax. And inside that one, you have to write one statement similar to C program. That's why after that there is a semicolon. The same thing you can expand for E subtraction T, right? And when it is expression derives term, then actually no action is mentioned because this is just simple reduction. No action is required. That's why. Now if I go to the term similar to this E derives E plus T, so here it will be T derives T multiplied with F. So again it will be $. This is my $, equals to, on the right hand side of the production, T is $1 multiplied with, so this is my $2. I do not need that one. This is my $3. So $3 will be there, and semicolon. Now for the division, it will be same, but one interesting fact regarding division is that you know that division by 0 leads to some error. That's why before writing $, equals to $1 divided by $3, I am making a check that if $3 equals to 0, then which means that by which I am dividing the factor, if it is 0, then there will be an error, division by 0. So instead of doing the division, I am reporting one error, YY error, division by 0. It will trigger this error function, auxiliary function. That's what I mentioned, that you please print there is an error. And since I am printing using cout and printf, that's why I need some header file like iostream or stdio.h, etc. Now, is it clear? I believe that's why I am including this one. String.h is included, although currently I am not using that one. But if you manipulate with the string specifically for this error message, then you can include that one. But as you understand, for the parsing process, that string.h or iostring is not required. Finally, for the factor, so this one is f derives within parenthesis e. Now here this is my 1, this is my 2, this is my 3. What is the action? This parenthesis just change the precedence of the operation. Otherwise, it do nothing. That you understand? So this $$ will be $2. So $$ will be $2. Why $2? Because you see that this E is actually $2. $1 is opening or left parenthesis, and $3 is closing or the right parenthesis. When it is the unary minus, then my production is F derives minus T. Sorry, my F derives minus F. That is what is written here. Now this is my 1 and this is my 2. So the action is $$ equals to minus $2. So $2 will come here. Okay. Now it is more or less complete because I have the number, I have expression, term factor, I have the production rules and the action corresponding to that production rule. Do you have any question from this or up to this? Okay. Now, every terminal and non-terminal has an optional attribute. Regarding this attribute, more details we will be discussing later when we will discuss IR and others. Multiple types of attributes are possible. They are bundled in a C union by % union. An attribute is associated with a terminal by the % token invalid number. That is what I mentioned. An attribute is associated with a non-terminal % type invalid term. Now you see the difference between terminal and non-terminal. For terminal it is % token. For non-terminal it is % type. For terminal I am assuming the number because I am dealing with the calculator here. But when the scope will increase, so characters or other things will come or floating point, etc. Then accordingly I have to make changes. But for the timing it is fine. So for non-terminal, so term, expression, factor, so for each of them there is one type. So actions, every production rule has an action, C code snippet at the end of the rule that fires when a reduction of the rule takes place. In an action, the attribute of the left-hand side, non-terminal, is identified as $, and the attributes of the symbols on the right-hand side are identified as $1, 2, 3, counting from left to right. That's why I mentioned, say, when an expression is something like E derives E plus T, then for the left-hand side it is $. For the right-hand side it is $1, $2, $3. $3 is for T, $2 is for addition, $1 is for E. Left to right count. Missing actions for productions with single right-hand side symbol, factor derives number, imply a default action of copying the attribute. So $, equals to $1. That is very simple. So F derives num. Now you know this is my $, and you know this is my $1. This is just nothing but the assignment step. Okay. Now this is the header file. So it is generated by the Bison when you will compile. So key features I am explaining to you. So this number is 258. So just to avoid the collision with the ASCII table, so extended ASCII table, as you remember that it varies from 0 to 255, extended ASCII table. So just to avoid the collision with that one, that whether that particular number belongs to some character or not. So the number, it is starting with 258 and it is defining as 258 number. And rest of the things are just to define statements, and they are so they are generated by the Bison program, Bison utility. Now y.tab.h is generated by Bison from cal.y to specify the token constant and attribute type that I mentioned in the previous slide. I'm going to there. So here and here. Okay. y.tab.h is automatically included in y.tab.c and must be included in cal.l so that it can feature in lex.yy.c. So you remember when we demonstrated cal.y, then at the C declaration part we included y.tab.h, and I mentioned that it will be generated by the Bison. So you need not have to worry about the content, but you need to include this one so that you can use this one. Now the symbolized tokens are enumerated beyond 256 to avoid clash with ASCII that I mentioned. Union has generated a C union YY type. Line directive are used for cross-reference to source files. This helps debug messaging, so which is mentioned in line 8. YYLVAL is a predefined global variable of YYS type, extern YYS type, YYL value. This is used by lex.yy.c. In case you forget, let me remind that if you write say cal.l and compile with flex, we use flex, then by default lex.yy.c is generated. Okay. So this is the same program I have shown you. I mentioned that y.tab.h is required. To include here, it will be generated by the Bison. In the previous slide, we mentioned that it is generated by the Bison indeed. And math.h is not used right now, but it is included in future. If we do some mathematical related calculation, we'll do that one. Oh, okay. So here I am using A2I. That's why math.h is also required. So this A2I actually what it is doing, that corresponding to that digits, which one is read. So when it is reading, so it is reading as a text. So I am converting that text to some integer value, and this yyLval.inval is my attribute. I am storing that information there, and I am returning the number. Now either you can write your own small program in order to convert the text to the number, or you can use this A2I math function, and for that you need to include math.h. It's up to you. The rest of the things are same as the previous one, so no need to discuss. y.tab.h is automatically included in y.tab.c and must be included in cal.c so that it can feature in lex.yy.c. YYLVAL is a predefined global variable of YYS type. So attributes of terminal symbols should be populated in it as appropriate. That is my YYLVAL.inval, and that is being populated by YY text when I read an integer. So I'm going to the previous slide. You see that here the pattern I noted is integer constant, because it is 1 through 1 through 9 in one number of time, and then 0 through 9 any number of times. So positive closure and neat closure. So this is an integer constant. Going to next slide. When it is converted from the text, because when I'm reading I'm considering everything as a text, when it will be converted to A2I, alphanumeric to integer, then that content is stored here. Now recall in cal C we specified %inval number. Now inval is binding to that number. Okay. One more thing, that new line and any character except that space, tab and integer constant, you are returning that particular character, and you are returning only one single character following the ASCII code. New line is not treated as a white space but returned separately so that cal.y can generate error message on line number if needed. So it says that it's true that space, new line, tab all are of similar kind. We can return all of them or have no action corresponding to that. But if you keep on returning the new line, then internally you can manage one variable to count how many new lines has been returned. And if you know that how many new lines has been returned, then if there is an error, then you know that at which line the error is occurring. So whenever you will fire some error message, that division by 0, like what we mentioned in the previous slide, for division you need to check that whether it is a division by 0 or not. If it is a division by 0, then you need to report that it is a division by 0. Now, if you have the count on how many /n or new line you have encountered so far, and if you have one variable which will keep track of that information, that new line information, then you can specify correctly at this line I am facing one division by 0. Okay, so that's why /s is important, because it can help you to keep a track on the line number. So whenever you face some error and showing some exception or error message, then you mention at which line you are facing that one. But that is not required for space or say tab. That's why for space and tab there is no action. I'm going to previous slide. For space and tab, it is semicolon, no action, ignore white space. But for /n, so I am returning that text. And also for dot, it says that any other character you are returning. So if you wish to report that I got some unwanted or illegal character which should not be as part of my program, then you can also display that one. That's why dot is also returned using YY text 0. It is not being consumed. Okay, because say some mistakenly some character has been printed in between your program, so that is an error, right? It is not following the program syntax, so you need to report that information. So I cannot ignore that. What I can ignore is space and tab. So this is the flow. Now you are in more better position to understand what you need to write. So previously we demonstrated lex file or flex file .l. Here .y. This is my Bison file. So only these two things you have to write. Now my lex.l using flex utility by default will generate lex.yy.c. And when it will generate that one, it will also include one has include operation that includes y.tab.h. Because in .l you mentioned include y.tab.h. I am going back. So here in this line you included y.tab.h. Going next. Since it was included here, so after the flex utility, it will be in the lex.yy.c. And who will generate y.tab.h? It is the Bison. You see the arrow. So Bison will take my yacc.c or my bison.c as input. By default, it will generate two files, one header file y.tab.h and another .c file y.tab.c. Now the GCC compiler will take lex.yy.c, the output of flex utility, y.tab.c, the output of Bison utility, the header file y.tab.h as generated by Bison library function and flex library function in order to generate the a.owl or executable file. Now what is the role of this executable file? As of now, as part of the compiler design, I have done two steps: designing the scanner or lexical analyzer and designing the parser, my Yacc.c. So if I give some source code as an input, although I wrote it as .c, but you can consider some source code which follows the rules as laid down by the patterns of lexical analyzer and the grammar production rules as suggested by this Bison program. Following that, if there is a source code, then that source code will be taken as input by this executable file a.out and will generate the executable file which you can run and you can generate the result. So here at the bottom, so steps are mentioned. First you write flexcal.c. So Yacc, or I prefer Bison, to convert cal.y. Now separately you compile this lex.yy.c and y.tab.c. Finally you combine lex.yy.o, y.tab.o minus lfl. So regarding this flag, I am including for Flex and Bison library. It may vary from system to system. You please check which is good for your system and accordingly you include. Okay. So that is in general the Flex Bison flow and the build command. Here is a sample run for our previous Bison code. So a.out was our executable file generated. In the terminal, if I run, then it will wait for some input. Then 12 addition 8 dollar indicates the end of the string. If I do that one, then it will print 20. If I type using the same code, 12 plus 2 multiplied with 45 divided by 4 minus 23 multiplied with 7 plus 1 followed by dollar, end of the string, then it will print minus 150. Now this equals to sign is actually printing, because in my printf statement I am giving equals to. I am going back to the action states of my Bison. Here you see that, let me erase everything. Here you see in the printf, what is printing? Within double quote equals to %d/n. That's why going to the next. Here, that's why this equals to is being printed. If you do not give that one, then it will just print 150. So in Linux, if you type BC most of the time, if it is installed, then it will open one calculator mode. Same thing you can do there also. You can write say 12 plus 8, and for them it is not the dollar, actually it is the new line which indicates the end of the expression. Then it will print 20. Okay. So in the next slide, let us go for working of this 12 plus 8 using the two stacks. So two stacks we are maintaining here. At the bottom you see first here. So I am starting here because my expression is 12 plus $8. Okay. So this is my num. Subscript 12 indicates number with the value 12 plus number with the value $8 at this position. This is my grammar rule for the simple calculator I mentioned, and corresponding to each production rule, what was the action encoded in my Bison program is also mentioned here. Printf %d $1, it was just a printf statement. For addition, $$ equals to $1 plus $3. Y3 that I explained to you. So all those are listed here. Now when it is num12 plus num8 then I'm scanning from left to right. I see num12. It is num. So num will reduce to f. So here in my stack you see num has converted to f. No change on the value 12. Then when it is converted to f, following the production rule 7, I am converting f to t. So first one, num to f, was following the production rule 10. This is following the production rule 7. F to t. No change on 12. If I look at the parts tree from num 12, I am reducing to f, then f is reducing to t. So please note it down, as I mentioned during the parser, that the subscript doesn't mean that it is a different non-terminal. Subscript indicates different state of a non-terminal. So when I say T1 and T2, both indicates turn non-terminal or T non-terminal, but T1 indicates one state, T2 indicates another state. So to differentiate between these two, the convention we are using by giving some subscript 1, 2, 3 like that. You can consider that says about the different states. Okay. Now after this T, then T will be reduced to E following production rule 4. So all these things we have done when we studied that parsing table, parsing process, etc. So T to E I am moving. As of now, no change on 12. Then up to here I reached, E has changed. Now I will shift to addition. So addition I shifted and addition is pushed here. Then I shifted further and num is pushed. So num is here and 8 value is there. Again, following the 10th production rule, I am changing from num to f. Then following the 7, I am changing from f to t. Okay, now here num I have got, then num to f, then f to t I have got. Now you see in this stack e plus t is there, and corresponding to the value is which is stored in the attribute int val is 12, and for t it is stored 8. Now the production rule I need to use is 2. From 2 I am moving here e plus t to e. So e plus t to t I am moving here. And for production rule 2, what is my action? $$ equals to $1 plus $3. Now this is my $1 and this is my $3. After the addition, I am placing that one back here in the $, that is my 20. Now I will use the production rule 1 to reduce it to S. From here I am reducing to S. And what is my final output? Production rule 1 will print. Which one will be printed? Which is in $, that is 20. 20 will be printed using equals to symbol here. Okay. So up to this or in this slide, do you have any question? Okay. So this is simple. Now we will move on to the programmable calculator, but I think today we don't have much time. So we will continue this programmable calculator on the next week. So do you have any question from today's class or any other question? Okay.
So what will be the syllabus for next week?
Yes, next week we have a class, and the class will include the syllabus of up to parsing.
Okay, sir.
Okay. So thank you very much.
Sir, in the production rules, we have